set the basis for the discussion about what makes the cloud different than traditional infrastructure and traditional approaches to working with IT. With traditional IT, if you ever want to do anything, you need to figure out what kind of resources you need to do it. You need to figure out what kind of computing power you need, what kind of memory you might need, network connections, software, all these sorts of things. And before you can even get started on a project, you likely have to make some sort of capital expense. So you have to spend some money on infrastructure, you then have to order it or somehow get it, install it, and secure it, all these sorts of things. This takes time, and it costs money. Whereas with the cloud, if you have an idea and you want to try something, and you know what kind of infrastructure you need, perhaps you need a GPU or perhaps you need a server with a lot of memory, you can just turn on a virtual server for an hour and try out what you're trying to do, or for a few hours, and use it for as long as you need to, and then when you're done, you can turn it off. So if your experiment failed, you're not that much poorer than you were at the beginning because you didn't have to order all this infrastructure and spend all this time setting it up. Just keep this in mind as I talk about open data, because this approach of the cloud and allowing people to experiment at really low cost has had a dramatic impact on how applications are developed, how services are provided. Any of us with smartphones and who use services like Airbnb or Netflix and things like that, we're able to do these sorts of things because of the cloud has allowed these companies to experiment and scale very, very efficiently with very little risk. Now, I also like to answer the question, why does AWS even have an open data program? Why does it matter to us? The short answer is because it matters to our customers. We have a lot of customers that operate both on the supply side and the demand side of open data. So we have public sector customers, whether they're meteorological agencies, like I mentioned before, or universities, that they're producing massive volumes of data, and they're spending a lot of money to produce these volumes of data explicitly for the purpose of sharing them with other researchers. Their whole reason to exist and their whole reason to produce these data sets is to get them into the hands of as many people as possible to drive research and to drive innovation. Then on the other side of the coin, we have customers who are building consumer applications or business-to-business applications, or they might be doing their own research, and they depend on access to government data. Without access to government data, they simply can't do their jobs. And we serve both of these customers, both of these sets of customers. Now, when I talk about open data in this context, I want to be clear that I use a quite broad definition of open data. Some people believe there's a definition of open data, which is that open data is only data that is publicly available without any fees associated with acquiring it or accessing it, with no license restrictions other than asking for attribution in return. We use a much broader definition of open data, which is that it's data that is made as open as possible by whoever's providing it. The conversation around open data and the importance of sharing data publicly is a broad conversation, and we want to include as many people in it as we can. We don't want to exclude people who want to share data as openly as possible, but can't because it might contain patient data, for example. We work with a lot of customers who share cancer genome data, so they're trying to accelerate cancer genome research. They're opening up their data, but they can't open it up to just anybody in the public because obviously the data contains cancer patient data. You don't want anybody to be able to access this sort of stuff. So it's controlled access, it's somewhat secured, but there are no costs associated with the data. There are no licensing fees. And when I talk about open data, I'm including these kinds of data sets into that conversation. Now, when we think about where we can add value to the open data community, we take a look at ourselves, look deep down inside and figure out what are our strengths and what do we have to offer. And as an infrastructure provider, we have a pretty elegant solution for making data more accessible and easier to work with. And it has to do with data acquisition. The conversations around how to open up data, how to share data are extremely vast and at times complex, right? There are issues you have to think about in terms of licenses, so these are legal issues. You also have plenty, if you want to get into any variety of fights with people on the internet, you can talk about standards. that you should use when sharing data, appropriate file formats and metadata and things like that. These are all conversations that are happening. They're important conversations, and we're happy to let our customers experiment and open up data in whatever formats and ways that they want to, as flexibly as possible. But where we have something to offer is when it comes to data acquisition. If users can acquire data and get access to data much more quickly, they can spend time actually doing analysis rather than just waiting for data to download. And I'm going to explain why this is important in the coming slides. So first of all, I'd like to share this quote, which is that about 80% of a data scientist's time is spent just preparing data for analysis. This is from a book called Data Driven, and it's a really short book. If you have a Kindle, I think it's free. Last time I checked, it was free on the Kindle, but I recommend it. It's a quick read, and I'm really glad that DJ Patil and Hilary Mason wrote this book, because it allowed me to quote this 80% figure as though it were something accurate and official. I'm not sure if that's really true. But every time I share this figure, nobody disagrees with this idea. Anybody who's worked with data, who's downloaded data from some public website and has tried to figure out what they were working with knows that preparing data can take up a lot of time. And we have a term, Max Peterson actually used this term on stage this morning that you may have noticed, which is undifferentiated heavy lifting. This is a very Amazonian term. We use this internally at Amazon all the time to describe the work that our customers have to do that they wish they didn't have to do before they can do the things that they really want to do, or the things that they're good at. And if you look at the cloud through this lens, you'll see that everything that we do is designed to remove undifferentiated heavy lifting from our customers' lives. So we don't want anybody to have to worry about running out of storage. We don't want them to worry about having to scale their servers. We can automate that kind of thing. You certainly don't have to worry about buying servers and buying storage and securing those sorts of things, cooling them, powering them, et cetera. Everything that we do is designed to relieve our customers from the undifferentiated heavy lifting that keeps them from doing what they're really good at and the things that they dream of doing. And this is particularly important with data, especially as data volumes keep getting larger. So traditionally, if you ever want to work with data, you have to get the data from wherever it's hosted and get a copy of it and move it down to wherever your computing power is. So that might be your laptop. You might have a more powerful computer. But regardless, there's some data transit that has to take place. And this is the traditional model of sharing data. Many people have experienced downloading data from an FTP server or from an online portal or something like that. Now, also, all of us have probably experienced, if you've upgraded your phone over the past few years, so let's say over the past 10 years, you may have had a smartphone, you may have upgraded one. Every time you upgrade your phone, the pictures that you take with it are bigger, right? So the sensors on your phone have become higher quality, and they're producing greater volumes of data. This is not just happening on your phone. This is happening everywhere that we're gathering information in the world. Cities are instrumenting themselves with Internet of Things sensors that are gathering all sorts of data about operations. We have plenty of government-funded Earth-observing satellites and other weather sensors that are producing greater volumes of data. Max also mentioned, and I won't get the statistic right, but he talked about how researchers in Munich have reduced the time required to sequence a genome, I think from 20 hours to 3 hours. It was something like that. What that means is that you can sequence a lot more genomes. You're going to be working with greater volumes of data. And what's happening is that as the volumes of data in our lives increase, the ability to move large volumes of data over networks is not getting easier at the same rate. And also another interesting thing that's happening is that more and more people have access to really powerful computers. Again, using the phone example, a lot of you probably have phones with GPUs on them, which is totally crazy. I mean, if you told somebody 10 years ago that, yeah, you're going to have a GPU in your pocket, it's pretty remarkable. And you have a GPU in your pocket because it's good for gaming. I think that's one of the main things that drives this sort of thing. Or maybe applying Instagram filters or something like that. But so there are consumer reasons to have this kind of processing power. But what it also means is that people have the power to work with and analyze really large volumes of data that just wasn't possible before. So if any of you are in a situation where you're being required or asked to share data because of a policy or because it's your mission, you're likely contending with the fact that you have more data to move around, and you have more people who have the ability to work with it. You likely have a more diverse audience of people who want to work with it as well. So the cloud approach, and this goes back to the very first slide that I showed, is that instead of moving data from wherever it's hosted down to wherever your compute power is, if data is available in the cloud, you can deploy compute resources right next to it, right where it is. And this seems simplistic. It is a little bit simplistic, but it's a huge impact, and I'm going to explain this in a little bit. So the beauty of this is that if you have any kind of code that you want to run on any kind of server that you want to run, so you can run Windows servers or Linux servers, you can turn those on in the cloud and analyze the data without moving the data very far. So you can work with the data without having to download and store your own copy. Now, there's an immediate obvious benefit to this approach, which is that if you ever want to work with a large volume of data, it's much, much easier to work with that large volume of data if it's in the cloud. If we just use a terabyte of data as an example, if you have a 50 megabit internet connection and you want to get a terabyte of data, that's going to take you about 2 days to download. And that's if you can use all the bandwidth to get it. And you'll hear at AWS summits all the time, we talk about like petabytes of data, and these, we talk about terabytes and petabytes very casually. So a terabyte takes 2 days to download with a pretty good internet connection. A petabyte is 1,000 terabytes. And in my experience, very few humans, and I'm pretty sure this has been like research, very few humans have the innate ability to comprehend orders of magnitude and jumps in orders of magnitude. 2 days times 1,000 is about 5 years, right? So if you want to work with a petabyte of data, there's no way you're going to get this over a network. And no one does that, right? So we don't, in fact, our solution to moving huge data sets around is we have a snowball. If you're familiar with a snowball, we will just ship massive hard drives around because it's a lot more easier to do it. And if you've got a lot of data, we have a truck, the snowmobile, where you can fit 100 petabytes of data on, and we'll literally send you a truck full of hard drives to copy your data out. So you don't do this stuff over the network. You have to get data in the cloud before you can work with it. Now, the other beautiful thing is that you can run your own code in the cloud without having to download and store your own copy, without having to take all that time to download data. But we also have managed services like Amazon Athena, which is really useful for running SQL queries against large volumes of data, or Amazon EMR, which allows you to run MapReduce workloads more easily in the cloud. So we're continually adding new services to the cloud to make it easier to work with data. And then you can just scale this stuff up. So if your idea works and your research is going well, you can bring on more servers. If it's not, you can scale them back down. It's no big deal. So in summary, these are the advantages. This is why open data on the cloud really matters, is because when you're sharing data in the cloud, as opposed to the traditional approach where you're asking people to download it, you can accelerate research by making it much cheaper for people to work with data because they don't have to spend the time or the money to have local infrastructure to copy data, which allows them to experiment much more quickly. We're continually adding new tools to the cloud, so if data's there, as we add new computing power, new computing capacity and services, we're potentially unlocking more potential from that data. And I have some examples of this that I'll show in a moment. And then finally, this is sort of the first point on the slide, but I haven't mentioned it before, which is that there's millions of people use AWS every month. So if you're working with data and you want people to be able to work with data, if it's been made available in the cloud, you're able to tap into a very large and growing community of users who already know how to use AWS and who are collaborating on tools together to work with data in the cloud. Oftentimes, if you have any questions, it's just a very simple search query away to find your answer, perhaps on Stack Overflow. Now, we have a program called the AWS Public Dataset program that we use to experiment with ways to do this, right? So it's very easy to say, okay, well, just make your data available in the cloud, and then everything will be great. It's true, there are obvious benefits that I just described to sharing data in the cloud, but doing it right actually requires a lot of work and it requires a lot of experimentation. So the Public Dataset program is a program in which we collaborate with data providers on ways to share data openly in the cloud. And this is a way for us to experiment with them to find out what are the best practices, what are the patterns that we should be using when sharing data in the cloud. And if you go to registry.opendata.aws, you will go to what we call the Registry of Open Data on AWS. We call it RODA. And you can find data sets that have been shared there through the program. This is what it looks like. We also have tags, so you can browse data sets by tag. Satellite imagery is a popular tag, and in fact, I'm going to talk now a little bit about what some of the stuff we've been doing with satellite imagery. So what you're seeing here, this is an image of Wellington, New Zealand. We actually have a sort of a subset of the public dataset program called Earth on AWS that's focused specifically on earth science data sets that are available in the cloud and some cool things that people are doing with them. So this is Wellington, New Zealand. It's not actually pink. This is a visualization based on satellite imagery to highlight healthy vegetation. So there's a lot of healthy vegetation in Wellington. This is why they filmed Lord of the Rings in New Zealand. It's just a very beautiful part of the world. And so this is an image that was created by the Landsat satellite. So Landsat is a satellite operated by the US Geological Survey that it produces imagery of the entire planet every 16 days. And I'm doing this with my hand because this is what the satellite does around the planet. It orbits the poles and just kind of like covers the entire planet every 16 days. And a few years ago, we started making Landsat data available in AWS for people to work with. And the results were pretty surprising to us. I mean, we knew that Landsat data was valuable data. We knew that we had a lot of customers that wanted to work with it. But when we were all surprised by how significant it was to make it available in the cloud and what people are able to do with it when we did. So to demonstrate this, first I show this graph from a guy named Drew Bollinger, who produced this graph for us, where he shows off here 90,000 points on this graph, which are 90,000 analyses that he was doing on Landsat data. And he's doing analysis very similar to what the previous image was, which was estimating the health of vegetation on different parts of the planet. And on the x-axis is the date on which he did the analysis, and on the y-axis is the time it took for him to do each analysis. And on the left-hand side, you see there's a sort of cohort of analyses that took longer. They're higher up on the y-axis. Those took about 350 to about 500 seconds each. And then we made Landsat data available on the cloud, and he was able to work with the data simply without having to move it very far. He was able to query the data much more precisely than it had before. And the time required to do each analysis went from, again, 350 to 500 seconds to about 20 seconds. Now this is significant. So that's, one time, that's a pretty significant time savings. You save somebody about 5 minutes or something. That's pretty nice. But he had to do this 90,000 times. And so we did the math on this, and we found out that Drew, because the data was available on AWS, was able to complete this project 150 days earlier than he would have the other way. Okay, so that's one researcher who saved 150 days and was able to spend that 150 days probably doing more sophisticated analysis or more high-value work than waiting for things to download. So that's nice. It's nice to be able to save researchers time. But there's another impact that we can see here, which is that if data is available in this way, where you can access it so efficiently with compute resources that are right next to the data in the cloud, is that you can provide services. You can actually create real-time web apps that interact with the data just through a browser. And this is an example of an application that uses Lambda. So Lambda is our serverless compute service that is able to go into Amazon S3 and pull out very specific pixels, very specific parts of the satellite imagery, and render imagery in a web map in real time. I'm going to go back to the previous slide again, just to give you a sense. Again, looking at the left-hand side, right, of the time required to process, if every time you dragged around that map, you had to wait 5 minutes for something to load up because some process was in the background just downloading data, you would not use that web application. It just wouldn't make sense. But in today's world, where people are used to really powerful web apps, this kind of thing just gets taken for granted. But what's really remarkable about this is, I show this animation all the time, and there's always there's like two types of people in the room. There are people who are like, oh, cool, it's a web app, like it's just like a map online. That's really neat. And then there are the people who, when they were in grad school, they had to order Landsat data on tape. That would take like weeks, and they'd have to like spend money to do it. And they're like, this is insane. So they've lived a life in which they only dreamt of being able to do something like this. And now this kind of thing is just we just take it for granted. It's kind of a funny thing about technology is that we take it for granted pretty quickly. And in fact, the guy who built this, his name's Vincent Sirago. He reached out to us. He's like, hey, I have this cool idea, this thing I can do with Lambda and the Landsat data. Can I get a grant? Because we have a research credits program where we'll support individual developers and researchers who want to try to do something kind of crazy and new. We'll give them credits. And we said, Vincent, this sounds awesome. We'd love to support it. How many cloud credits would you need to do this? And he did the math. He tried to figure it out, like how many Lambda functions you would need. And the number he came up with, I don't remember what it was precisely, but he just didn't ask for a grant because he's like, it's going to be like $10. So I just, never mind. So running something like this is really remarkable because Lambda is extremely inexpensive. It's just amazing how cheap it is to do this kind of stuff. Now, there's another sort of more sophisticated example. This is a service called Sentinel Hub. And this is written by, this is produced by a company called Synergize. Actually, they were on one of my earlier slides. It's a Slovenian company, and they build these SaaS applications. And what you're seeing here is very, behind the scenes is actually very similar to the previous slide, in that, and I actually don't know if you caught this, but like you can draw a polygon on a map, so you have a web map the way you're used to interacting with maps online. And you can find a part of the planet that you're interested in. In this case, it's a farm field, and you want to look at some crop on the farm field. And this will loop over so you can see what's happening again. But you just draw a polygon specifically around what it is that you want to look at, and then that'll kick off in the background. You click on something and you say, okay, analyze this part of the field. And what it's doing is it's, again, triggering a bunch of Lambda functions that are going to S3 and saying, tell me about this patch of the planet. What's the vegetation like? What are the vegetation indices here? And then also, I want to look back a year. I want to look back, 2 years, 5 years. Give me all the data that you have that we can use to measure the vegetation of this part of the planet right now. And it does that. And it does all this math and processes it all in real time. And the reason it's able to do this is because the data is just right there in the cloud, and it's organized in a way that allows for programmatic access. It's really, really cool. Sums up these fonts. But anyway, hopefully, what that URL says is opendata.aws/sustainability. So if you're interested, we have a thing called the Amazon Sustainability and Data Initiative. This is something that we've learned actually since we launched the Landsat data, is we found that the applications of opening up large volumes of satellite imagery or meteorological data in the cloud can have huge impacts on sustainability research. And so we teamed up with Amazon Sustainability. So this is the organization for all of Amazon that focuses on Amazon sustainability goals to collaborate together and figure out what can we do to ensure that sustainability data is easier for people to access. No matter who's using it, whether it's other corporations or researchers, we want to make sure that people have access to those kinds of data. And we've opened up, again, all sorts of meteorological data and satellite imagery, as well as air quality data and hydrological models. One example of how this data is being put to use is the Africa Regional Data Cube. So this is a specific product and service that's built for Kenya, Senegal, Sierra Leone, Tanzania, and Ghana to address food security issues and other environmental issues in those countries. And this is particularly interesting to me and very gratifying to me. I mean, this is precisely what we're trying to do with the program, is make data available in ways so that many different audiences can come up with different ways of working with it. So the examples I showed before are, they're awesome examples, and Synergize has built the Sentinel Hub, which is a tool that satisfies a lot of people's needs. But certainly, it's not going to satisfy everybody's needs. And the Africa Regional Data Cube is designed to satisfy the needs of 5 particular countries right now. It's a somewhat bespoke product for those countries. And that's the beauty of making data available in this way, is that, and this is also the concept behind like what we call a data lake. You might hear the term data lake a lot at this summit. You hear it a lot these days. It's a buzz term. But like the point of a data lake is that you have a bunch of data that's hot and ready. It's available programmatically. It's available for programmatic access, and anybody can come in and draw on it in any way that they want, rather than saying, here's some satellite imagery, and here's the only tool you get to use to work with it. Like, this is the only way to use it. Instead of that, we can say, here's some satellite imagery, go crazy. Take whatever approach you want, use whatever biases you have, focus on the things that you want to focus on the user communities that you need to focus on, and build the tool that's best for them. And the Africa Regional Data Cube is one of these things. And as far as I understand, it's been quite successful, and now other countries want similar things as well. And they can build them because they can all draw from the same data sources. And then one final example of this, this is another example driven by Sentinel Hub, but it's a thing called the Blue Dot Observatory that Synergize created in collaboration with the European Space Agency. And I share it because, I mean, this is a very cool application, first of all, is that it's designed to use satellite imagery to measure groundwater around the planet. So you can measure lakes, rivers, things like that. And because they don't have to worry about paying to host all the data required for this, again, images of the entire planet over and over and over again, they're able to monitor around 7,000 bodies of water for €6 a month. This is the kind of innovation experimentation that we're really gratified to be able to support, and it's always just astonishing to see what people are able to come up with when we give them access to data without telling them how they should work with it, right? One of the things that I frequently talk about, and sometimes I often talk about democratizing access to data. And when we talk about democratizing access to data, or when I talk about it, it very specifically means to expand the audience of people who can work with the data by the sort of largest volume of people, but also the most diverse audience of people. Diversity is incredibly important to working with open data, because if you're going to produce some sort of data asset and you want to get as much value out of it as you possibly can, you want to make it available to the largest, most diverse audience possible, because they're going to approach it with different perspectives, different preconceptions, different biases, and also, very significantly, I think this is important, different budgets. Right? So some people are going to come at it and be like, oh, this is really cool. I have a huge budget, so I'm just going to fire a bunch of GPUs at this thing and tons of memory and run a bunch of applications that I'm used to using, and it'll be really fast, and it'll be great. I'm very happy for those people. I think it's really nice. But then when you get a small Slovenian company that might not have that same budget, or just a student somewhere, they're going to look at the data and think about the possibilities and the opportunities of working with that data in a completely different way. And they're going to come up with things that we never would have thought possible. And in fact, I mentioned before Lambda. So AWS Lambda is our serverless compute service. And the way it works is that if you can trigger an event, you can fire off a Lambda function. You can make a Lambda function occur. So on that map that I was showing before, that was the guy's like dragging around the map and it's rendering the imagery. What's happening there is as you're interacting with the browser and moving the map around, that's causing Lambda functions to fire. You're creating an event that will then communicate to Lambda and say like, hey, run a Lambda function that can go in and look at S3 and see if there are any pixels in this bucket for this part of the planet and send them back and render them and blah, 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 blah. Now, Lambda came out after we made the satellite imagery available. And just, as a case in point of the importance of diversity, and intellectual diversity when making data available, is that when Lambda came out, I was like, wow, Lambda's really cool. That'll never work on satellite imagery. I was like, oh, that's just not going to happen, because the imagery's too big, and the Lambda functions they're quite small. They're limited in terms of how much memory they have and how much data they can actually process at a time. And I'm so glad I was wrong about this. It's really why this is so significant. Is that I'm like, well, that won't work. And then sure enough, it took about 4 months or something like this, but developers figured out how to make it work. They figured out how to use open source libraries to get the right code into Lambda functions and to run fast enough, and then also to make the very precise and accurate queries that they needed to make in order to get only the data they need so that it could be processed within a Lambda function, within the limitations of a Lambda function. And I can't say how happy I am to be wrong about stuff like this. It's just really, really cool to be able to see what happens when you give people access to so much data and then let them surprise you. And with that, I'm going to hand the time over to my colleague Danielle, the awesome solutions architect, who is going to talk about ways that you, especially if you work in government, might be able to use open data yourselves to serve citizens. So thank you. Thanks, Daniel.
Hello, good afternoon. My name is Daniel. I'm a solution architect in the public sector team. And at this point of the session, what I wanted to take you through is through the benefits of integrating open data in your own architectures, in your day-to-day architectures. So you don't see open data as a kind of an isolated portal, kind of an isolated tool, but something that can really help you on your day-to-day process. I will do so by showing a couple of examples, and I really hope that these examples foster your imagination and new use cases that make sense on your environment. So let's kick off. The first example I have for you is imagine for a second that you are a city, town hall, a county, that you need to apply traffic restrictions, which are a very common scenario these days. So in this case, you probably need to apply these restrictions based on certain parameters. I don't know, probably it's air pollution, it's traffic levels, it's plates numbers, odd numbers, even numbers, whatever parameters you need to do, but you need to apply these restrictions. So in order to do so also, you will need to tell your citizens, to warn your citizens in advance that the restrictions are going to take place, so they can prepare ahead, they can prepare for alternate transportation methods, different routine. In fact, if you want to keep them happy, you will do this quite in advance. So it just happened the same day, the citizen will not be very happy. So in order to do that prediction of the restrictions, you very likely have a system with an architecture similar like this. Or if you don't have it, you're thinking on having one of these. So this is an architecture built on AWS, on AWS services. This is a resilient, cost-effective, and scalable architecture, but that's for another chat. What is important here is the steps of the system of the architecture. As you can see here, in the first step, you will probably have information, you will probably have data and traffic history, collisions, a lot of data about your city, about your environment. And at the other end of your architecture, you will have an algorithm that will try to predict with certain variables that you will need to apply restrictions or not. In the middle, what you will have is a transformation process from the data that you have to the data that can really train an algorithm. You will probably need to transfer your data from a particular format to another in ways that can be fed to your algorithm. So with this, of course, you can get an algorithm that will help you predict with certain accuracy if you're going to apply restrictions on your traffic in a particular day. But we have seen in the field is that when you enrich the data that you have with data coming from public sources, from open data, whatever it is through APIs, whatever it is downloading the whole data sets and mix it up on your ETL process down in the middle, we see that the accuracy of your models improve a lot. So for example, that you include data about news sentiments analysis. Just for example, that the petrol price are going high, going low, that will have an impact on your traffic and the traffic that you expect, and that will have an impact that your algorithm will be able to assess. Let's say, for example, that you take into account global climate conditions, because some day or the other, that will have an effect on your local air pollution levels. So that's something that the algorithm will use also to provide more accuracy on the predictions that you're going to make. Take, for example, another thing, this, the weather itself. The weather is very important. So you mix up your data with weather conditions, you're going to have very well-explanatory reasons for your algorithm to predict better and with more accuracy as well. And one particular example of this kind of architectures is the city of Louisville. The city of Louisville was spending a lot of money on traffic analysis. They were making changes on the road configurations, traffic signals, traffic stop lights, and they were spending a lot of money in getting traffic analysis just to understand the impact of those changes. Those analyses were static analysis, so just I made the changes, it was to happen. It's not real time, not dynamic, and it could take weeks for them to get them. So it was clearly not working for the purposes. So they needed to think of something else. And what they did, so they started noticing that they had data about their environment, data from historic traffic, like for example, history of traffic collisions. They have a lot of data about their own environment. And they started to mix this data or enrich this data with data coming from Waze, the traffic app. I guess you all know Waze, from their Citizen Connected program. And within the AWS platform, they started to enrich this data to create new data based on the combination of these data. And up to today, they have realized that they have a platform that is able to have a real-time dashboard information of their traffic. That is not only helping them to understand what's going on real time, but also to create real predictions on, for example, they are doing predictions on the collisions that's going to happen on a certain day. Predictions on many other topics. The other thing that they can do is, for example, taking account the safety for bikes, for pedestrians. They can also make predictions there. And overall, they can plan better for their emergency services, emergency recovery, and the rest of associated services. This is a really cool example. And they even took this further. They did something else. They created, on top of AWS, they created a template, an architecture that is publicly available in GitHub, and anyone can use it, that will deploy something that they call WARP. What we deploy is an architecture, a system that will kind of ask data to Waze every 2 minutes. It will get the data back. It will process the data. It will mix it up with the correlated data that you have, and will store it in a relational database. And with the relational database, it will be able to kind of create those traffic analysis in real time. They, for example, use tools, use templates in Power BI in order to have their dashboards on traffic information. It's a real cool example. It's public, so you can check it out on the AWS internet pages. So let me give you another example. Let's say you're still a city, a county, or town hall. You'll still need to somehow monitor your public assets, for sure. You need to know where your police cars are, your ambulance, your firefighter trucks, because when there's an emergency, you need to send the ones closer to the emergency. And you probably monitor this from a monitoring center, an emergency center, or something like that. And if you do so, you probably have a system with an architecture similar to this. Again, don't worry about the architecture itself. I'm going high level on the system. By the way, this is a serverless GPS system. So it's as Jed mentioned before, it's based on compute with no servers, so serverless computing model. We built something that doesn't have a server, but still works to ingest data from GPS. You may have a traditional approach with GPS running 24/7, but this is a really cost-effective and scalable approach. Either way, this is for another topic, as I said before. The important thing is the steps. So your assets will have GPS-capable devices that will be sending signals to your reception, to your GPS server. This server will receive the signal, probably will format the messages to have a unified messaging wherever it's coming from different devices. And the location will be stored in a database. Now that you have the data, then you need to visualize all of this information. Wherever you do it from a monitoring center, an emergency monitoring center, or maybe your workers do it from a mobile phone app, you still need to consult this data and be able to put that information on a map. And you know that digital mapping is not always cost-effective, it's not always easy to set up, it's not always available. However, when you use open data, you can create really rich visualizations in a very flexible and cost-effective environment. Like, for example, if you use OpenStreetMap, which is an open data set, probably most of you already know it, but it's an open data set that was created in 2004 with the intention of mapping the world and a collaborative effort to map the world, which the main output is the data itself, not the map, but still, you can use it to create tiles of the world and to create layers of information on top of it. So when you use OpenStreetMap, you can create rich visualizations with different layers of geographic information on top of it, and a very cost-effective and flexible way. And you can use open source tools like RenderD or Mapnik to create the tiles. So give me the map tiles. Let me give you an example. This is the DGT. The DGT is the government entity in Spain that handles or is in charge of all the road transportation for the country. This is a tool that many Spanish citizens consult just to understand what is the situation on the roads and so on. So as you can see in this blue dot, They're using OpenStreetMap to provide and to visualize this geographic information. They first of all use the OpenStreetMap dataset to create the map tiles with open source tool, and then they use it as well to put layers on top of information. And they are avoiding expensive digital mapping licenses, complex systems that get you locked in different products or different brands. They're using this, which is really open, innovative, and it's allowing them to have different initiatives because, as I said before, OpenStreetMap is a collaborative effort, and right now it has around 2 million persons contributing to it. It's really great, and I think that the DGT is really innovating with this. Another example, and this is my final example, and if you've been in the keynote, I think you've already seen this, and it's the one from the humanitarian OpenStreetMap. So what these guys are doing is really, really cool. So they use a device, AWS device, which is called Snowball Edge. Snowball Edge is a rugged device with a huge storage capacity, around 100 terabytes, and with a huge compute capacity as well, around 24 virtual CPUs, but can range even almost to 50. And as I said before, it's a rugged device. It can work in bad conditions and doesn't really need connectivity. It has APIs and connections, so you can work locally and consume the compute and consume the storage. So the whole team, they preload this device with information about the open aerial dataset, which provides aerial imagery of the Earth, and also with a portable version of the OpenStreetMap. And having this on site when there's a disaster, when there's a flooding, when there's a hurricane or some other natural disaster, really enables to have a workflow to assess and to better direct where you are going to direct your efforts to recover the zone. Because they also use drones that go through the affected area, taking imagery. They combine that imagery with the one that is already inserted in the device, and locally they can assess the impact of the disaster. They can assess where they're going to put the emergency needs first. We're going to send this or that to one particular area. It's really great. It's another public example, and you can check it out on the internet. So basically, this is where the two examples that I wanted to give you on how open data can really work with you and your day-to-day applications to help you better flows, better algorithms, and better visualizations. There are many other examples, and I hope that this is of some value for you. So, yeah, do you want to close off?
Thank you.
Thanks to you.
Thank you. So that's it, right?